Hello, I'm Robert Miles. Welcome to this recording of the Alignment Newsletter podcast. This is newsletter number 117, How Neural Nets Would Fare Under the TEVV Framework, published on the 16th of September 2020 by Rohin Shah. Highlights: Estimating the brittleness of AI, Safety Integrity Levels, and the Need for Testing Out of Distribution Performance, by Andrew L. John, summarized by Flo. Test, Evaluation, Verification, and Validation, TEVV, is an important barrier for AI applications in safety-critical areas. Current TEVV standards have very different rules for certifying software and certifying human operators. It's not clear which of these processes would be applied for AI systems. If we treat AI systems as similar to human operators, we would certify them, ensuring that they pass tests of ability. This does not give much of a guarantee of robustness, since only a few situations can be tested, and is only acceptable for humans because humans tend to be more robust to new situations than software. This could be a reasonable assumption for AI systems as well. While systems are certainly vulnerable to adversarial examples, the authors find that AI performance degrades surprisingly smoothly out of distribution in the absence of adversaries, in a plausibly human-like way. While AI might have some characteristics of operators, there are good reasons to treat it as software. The ability to deploy multiple copies of the same system increases the threat of correlated failures, which is less true of humans. In addition, parallelization can allow for more extensive testing that's typical for software TEVV. For critical applications, a common standard is that of Safety Integrity Levels, SILs, which correspond to approximate failure rates per hour. Current AI systems fail way more often than current SILs for safety-critical applications demand. For example, an image recognition system would require an accuracy of 0.9999997 at 10 processed frames per second just to reach the weakest SIL used in aviation. However, SILs are often used on multiple levels, and it's possible to build a system with a strong SIL from weaker components by using redundant components that fail independently, or by detecting failures sufficiently early, such that AI modules could still be used safely as parts of a system specifically structured to cope with their failures. For example, we can use out-of-distribution detection to revert to a safe policy in simple applications. However, this is not possible for higher levels of automation, where such a policy might not be available. Flo's opinion. While I agree with the general thrust of this article, comparing image misclassification rates to rates of catastrophic failures in aviation seems a bit harsh. I'm having difficulties imagining an aviation system that fails due to a single input that has been processed wrongly, even though the correlation between subsequent failures given similar inputs might mean that this is not necessary for locally catastrophic outcomes. Rohin's opinion. My guess is that we'll need to treat systems based primarily on neural nets similarly to operators. The main reason for this is that the tasks that AI systems will solve are usually not even well defined enough to have a reliability rate like 0.999999997, or even a couple of orders of magnitude worse. For example, human performance on image classification datasets is typically under 99%, not because humans are bad at image recognition, but because in many cases what the true label should be is ambiguous. For another example, you'd think predict the next word would be a nice unambiguous task definition, but then for the question, how many bonks are in a quoit, should your answer be, there are 3 bonks in a quoit, or the question is nonsense. If you're inclined to say that it's obviously the latter, consider that many students will do something like the former if they see a question they don't understand on an exam. Section Technical AI Alignment. Subsection Technical Agendas and Prioritization. Link AI Paradigms and AI Safety. Mapping Artifacts and Techniques to Safety Issues. By Jose Hernandez Arroyo et al., summarized by Rohin, with a hat tip to Hayden Belfield. What should prioritization within the field of AI safety look like? Ideally, we would proactively look for potential issues that could arise with many potential AI technologies, making sure to cover the full space of possibilities rather than focusing on a single area. What does prioritization look like in practice? This paper investigates and finds that it's pretty different from this ideal. In particular, they define a set of 14 categories of AI techniques. Examples include neural nets, planning and scheduling, and combinatorial optimization, and a set of 10 kinds of AI artifacts, Examples include agents, providers, dialoguers, and swarms. They then analyze trends in the amount of attention paid to each technique or artifact, both for AI safety and AI in general. Note that they construe AI safety very broadly by including anything that addresses potential real-world problems with AI systems. While there are a lot of interesting trends, the main conclusion is that there is an approximately 5-year delay between the emergence of an AI paradigm and safety research into that paradigm. In addition, safety research tends to neglect non-dominant paradigms. Rohin's opinion. One possible conclusion is that safety research should be more diversified across different paradigms and artifacts in order to properly maximize expected safety. However, this isn't obvious. It seems likely that if the dominant paradigm has 50% of the research, it will have, say, 80% of future real-world deployments, and so it could make sense to have 80% of the safety research focused on it. Rather than try to predict which paradigm will become dominant, a very difficult task, it may be more efficient to simply observe which paradigm becomes dominant and then redirect resources at that time, even though that process takes 5 years to happen. Subsection Preventing Bad Behavior. Link Avoiding Negative Side Effects Due to Incomplete Knowledge of AI Systems by Sandhya Sai Subramanian et al., summarized by Rohin. This paper provides an overview of the problem of negative side effects and recent work that aims to address it. It characterizes negative side effects based on whether they're severe, reversible, avoidable, frequent, stochastic, observable, or exclusive, i.e. preventing the agent from accomplishing its main task, and describes existing work and how they relate to these characteristics. In addition to the canonical point that negative side effects arise because the agent's model is lacking, whether about human preferences or environment dynamics or important features to pay attention to, they identify 2 other main challenges with negative side effects. First, fixing negative side effects would likely require collecting feedback from humans, which can be expensive and challenging. Second, there will usually be a trade-off between pursuing the original goal and avoiding negative side effects. We don't have principled methods for dealing with this trade-off. Finally, they provide a long list of potential directions for future side effect research. Subsection Miscellaneous. Link Foundational Philosophical Questions in AI Alignment, with Lucas Perry and Yasan Gabriel, summarized by Rohin. This podcast starts with the topic of the paper Artificial Intelligence, Values and Alignment from Newsletter 85, and then talks about a variety of different philosophical questions surrounding AI alignment. Link Exploring AI Safety in Degrees, Generality, Capability and Control by John Burden et al., summarized by Rohin, with a hat tip to Hayden Belfield. This paper argues that we should decompose the notion of intelligence in order to talk more precisely about AI risk, and in particular suggests focusing on generality, capability, and control. We can think of capability as the expected performance of the system across a wide variety of tasks. For a fixed level of capability, generality can be thought of as how well the capability is distributed across different tasks. Finally, control refers to the degree to which the system is reliable and deliberate in its actions. The paper qualitatively discusses how these characteristics could interact with risk, and shows an example quantitative definition for a simple toy environment. Section Other Progress in AI. Subsection Reinforcement Learning. Link The Animal AI Testbed and Competition by Matthew Crosby et al., summarized by Rohin, with a hat tip to Hayden Belfield. The Animal AI Testbed tests agents on the ability to solve the sorts of tasks that are used to test animal cognition. For example, is the agent able to reach around a transparent obstacle in order to obtain the food inside? This has a few benefits over standard RL environments. 1. The Animal AI Testbed is designed to test for specific abilities, unlike environments based on existing games, like Atari. 2. A single agent is evaluated on multiple hidden tasks, preventing overfitting. In contrast, in typical RL environments, the test setting is identical to the training setting, and so overfitting would count as a valid solution. The authors ran a competition at NeurIPS 2019 in which submissions were tested on a wide variety of hidden tasks. The winning submission used an iterative method to design the agent. After using PPO to train an agent with the current reward and environment suite, The author would analyze the behavior of the resulting agent and tweak the reward and environments, and then continue training in order to increase robustness. However, it still falls far short of the perfect 100% that the author can achieve on the tests, though the author is not seeing the tests for the first time as the agents are. For more information, you can read Building Thinking Machines by Solving Animal Cognition Tasks. Rohin's opinion. I'm not sure that the path to general intelligence needs to go through replicating embodied animal intelligence. Nonetheless, I really like this benchmark because its evaluation setup involves new unseen tasks in order to prevent overfitting, and because of its focus on learning multiple different skills. These features seem important for RL benchmarks regardless of whether we're replicating animal intelligence or not. Link Generalized Hindsight for Reinforcement Learning by Alexander C. Lee et al., summarized by Rohin. Hindsight Experience Replay, HER, introduced the idea of relabeling trajectories in order to provide more learning signal for the algorithm. Intuitively, if you stumble upon the kitchen while searching for the bedroom, you can't learn much about the task of going to the bedroom, but you can learn a lot about the task of going to the kitchen. So even if the original task was to go to the bedroom, we can simply pretend that the trajectory got rewards as if the task was to go to the kitchen, and then update our kitchen traversal policy using an off-policy algorithm. HER was limited to goal-reaching tasks, in which a trajectory would be relabeled as attempting to reach the state at the end of the trajectory. What if we want to handle other kinds of goals? The key insight of this paper is that trajectory relabeling is effectively an inverse RL problem. We want to find the task or goal for which the given trajectory is near optimal. This allows us to generalize hindsight to arbitrary spaces of reward functions. This leads to a simple algorithm. Given a set of n possible tasks, when we get a new trajectory, rank how well that trajectory does relative to past experience for each of the n possible tasks, and then relabel that trajectory with the task for which it's closest to optimal relative to past experience. Experiments show that this is quite effective and can lead to significant gains in sample efficiency. They also experiment with other heuristics for relabeling trajectories, which are less accurate but more computationally efficient. Rohin's opinion. Getting a good learning signal can be a key challenge with RL. I'm somewhat surprised it took this long for HER to be generalized to arbitrary reward spaces. It seems like a clear win that shouldn't have taken too long to discover, though I didn't think of it when I first read HER. Link Rewriting History with Inverse RL, Hindsight Inference for Policy Improvement by Benjamin Eisenbach, Xinyang Geng et al., summarized by Rohin. This paper was published at about the same time as the previous one and has the same key insight. There are three main differences with the previous paper. 1. It shows theoretically that maxent_IRL is the optimal, way to relabel data if you want to optimize the multitask maxent_RL objective. 2. In addition to using the relabel data with an off-policy RL algorithm, it also uses the relabel data with behavior cloning. 3. It focuses on fewer environments and only uses a single relabeling strategy, maxent_IRL relabeling. Section News. Link FHI is hiring researchers, research fellows, and senior research fellows by Anne LaRue, summarized by Rohin. FHI is hiring researchers across a wide variety of topics, including technical AI safety research and AI governance. The application deadline is October 19th. This concludes Alignment Newsletter number 117. For more information, you can go to rohinshah.com/alignment-newsletter, where you can find all the previous newsletters and also a spreadsheet of all of the papers and summaries that have ever been featured. Thank you for listening.